presentation. So today I'm going to talk about on a problem of isometry. So what it does, so the main topic of the talk is about a question asked by Aleksandrov. We will come to that later. But before that, okay, so we would start with a simpler question and try to answer that. And the nature of the talk is going to be an expository one. And I would say that, okay, a first course in linear algebra and analysis would be mostly sufficient to understand the content of the mathematical content of the talk. So, okay, let's start with basics. So let's start with the definition of isometry. So what is an isometry? So an isometry is a map that respects the metric. So what is it? So let's just write this down. So definition, 1 second. Okay. So isometry. So we have two metric spaces. So let be two metric spaces. A function f from x to y is said to be an isometry if it preserves the metric f So the distance between fx and fx2 is same as distance between x and x2 for all x and x2. Now isometries are very important, okay, for reasons that you would see for various reasons. So we will not get into that in this talk. So what I'm going to study in this talk is the isometries of Rn. Okay, so before we study that, let us just introduce a notation. Maybe we call it, we number this definition notation. So on Rn, we introduce several norms, the LP norms. This is when P is finite. Sorry. When P is finite, and this is the maximum of the magnitudes of its components when P is infinity. So on Rn, we define these norms. So the first question is this. Okay, so we have on Rn, we have this series of norms. Now, what are the isometries with respect to this norm? Okay, so you might have seen. So let me start with the standard case. That is when P is equal to 2. That is which is the case of the Euclidean norm. This you might have seen in your linear algebra course. This result. It says that so a map T from Rn we consider with Euclidean norm is an isometry. So if and only if there exists an orthogonal matrix and a constant B such that such that T is A of X plus B. So in particular, so a map on Rn with the Euclidean matrix is an isometry if and only first it's an affine map. Now it is not a priori clear why the map should be affine. The first thing. And the next thing is this: the affine map is determined by an orthogonal map. Okay, so this is something you might have seen in your linear algebra course. Okay, but what is much less known is that what will be the isometries when we consider the other norms. That is the LP norms. Okay, but P is not equal to 2. So this will answer in the next question. So theorem. So let P be not equal to 2. Okay, now what we do is this: a map T from Rn with LP norm so is an isometry if and only if there exists a matrix A. Now it comes from a different set. I will tell you what is this set. There's a matrix A and a constant B such that T of X is AX plus B for all X in Rn. What is A? So what is this set SPNR? So this is the set of all. So this is the spatial permutation matrix. The sign permutation matrix. So this is all non-singular matrix such that, okay, each element is either plus minus 1 or 0, and there is an exactly one minus 1 or 1 in each row and column. So this we write in the following way. For all ij. Okay. So now, when we consider isometries on Rn with LP norm P not equal to 2, still the isometry continues to be an affine. However, the map A that which determines the affine map is not a general orthogonal matrix, but it's a sign permutation matrix. But what is the relation between SP and R and OM? So remark. So note that. So this is a subset of ONR. Important. If you see how many elements are there, it is you can show that this set has 2 power n times factorial n number of elements. Okay, so how much? 15. Okay. So this is I give you a reference for this. So if you want to see the proof of this result, the reference would be an article by Chi Kwong Lee and Wasim So in American Math Monthly, and the volume number is, let me see, is 101 by 1994. Okay. So the crucial thing, an outline of the proof would be as follows. So how do you prove this? So first thing, you show that a map is an isometry. The map is an affine map. Now, how do you show that an isometry is an affine map? you just show that it maps a sphere onto sphere. Okay. Now this is where the compactness of sphere comes in when you want to prove that, and then you invoke whatever. So a theorem by Mazur and Ulam, which says that if you have an isometry that is also a surjective map, it is an affine map. Okay. So what you do is this. So once you show that it's a affine map, so there's a first step. The next step, you have to show that A comes. So A is a sign permutation matrix. Now this, how do you show that? So the crucial point is this. So step one, show that is affine. Okay. So step two, so you can always assume that T of 0 is 0 with the translation. So T is in fact linear after assuming that. Now step three is what is crucial, is if T is a linear isometry from R with respect to LP norm, its adjoint or transpose, whatever you want to say here, T star is also an isometry from Rn, but now with LQ norm is an isometry with where P and Q are conjugate exponents. Okay, so once you show this, now this is not a difficult, now this is not very difficult to prove. Now once you show that, the result follows. So I don't prove the result. I leave it as an exercise because this is not the main topic of this lecture. But I just wanted to share this result with you because this I find very interesting. Okay, and then the result follows. Okay, now good. Now let's come back to the main topic of the talk. Now, what does an isometry do? An isometry preserves distance. That is, so if the distance between x and y is r, the distance between fx and fy would also be r. Okay, so so what Alexandrov asked the following question, that suppose you know that a map preserves only distance 1. That is, the distance between xy is 1. If the distance between xy is 1, the distance between fx and fy would be 1 as well. So under which conditions the map is going to be an isometry? So what it says is that suppose a priori you know that the map preserves distance 1. Does it imply the map is an isometry? Okay, so that is so it was Alexandrov's question, and this is what we are going to so we are going to discuss in this talk. So let us write this down. This is Alexandrov's problem. I write this problem in the context of matrix space. However, we will discuss only in only for Rn. So let x be a matrix space. And let f from x to x preserve distance 1. So if a map preserves distance 1, we call it f satisfies DOPP. DOPP means distance 1 preserving property. Okay, suppose distance 1, that is distance between fx and fy is 1 when distance between xy is 1. Okay, when or under which condition the map is an isometry. Okay, we will see that Now, this is a looks like a very simple question, but we will see that there are many questions that remain open. And so I will mention some open problems at the end of the talk. So I will be happy if you want, want to think on those problems. Okay, so we will. So in this talk, we restrict ourselves to Rn. Okay. So let's start with the simplest case when n is equal to 1. That is in the one-dimensional case. Let's look at the Aleksandrov problem. So the simplest, so the case of, so maybe, okay. So case when n is equal to 1. Okay. We will see this. There is nothing to, okay. Now we will see this here. The distance preserving, so if a map preserves distance 1, it doesn't even have to be continuous, let alone being an isometry. Okay, so let me give you an example. So let us define f from R to R by, okay, so f of x is equal to x plus 1 if x is in Q, x if x is in R. Okay, so check that this map is not continuous. Clearly, f is not continuous. F is not continuous. But you see this, but f satisfies DOPP because f has a distance one preserving property. Because so if you take if you take two numbers as the mod of xy is equal to 1, then either both xy are rational or both xy are irrational, and hence it follows from the definition of f that mod of fx minus fy is 1. Okay, so I'm not writing this down, but is it clear to you? So if it's not clear to me, please feel free to ask questions. Okay, so I repeat, if you have two real numbers such that the distance between them is 1, then either both xy are rational numbers or both xy are irrational numbers, in which case the definition of fx immediately tells you this, that the distance between fx and fy is 1. Okay, so clearly, anyways, I'm not writing this down. So the next thing that comes up, that okay, so if you put some regularity condition, is it an isometry? Again, that is not the case. So because I give you one more example. I leave it to you to check that. So I would say x plus, maybe I give some alpha sine 2 pi x, maybe, right? X is alpha sine 2 pi x for all x in R. Okay. Okay. Now check that. Okay. Now alpha is positive. So let alpha is positive. So check that if satisfies DOPP, but if is not an isometry. In fact, it's easy to check that if is not 1, 1. Okay, so we see this in the one-dimensional case. Aleksandrov problem doesn't have anything interesting to discuss. So let's go to the higher dimension. Okay, so the higher dimension, we have this very interesting result. Now this is quite counterintuitive, and this was proved before Aleksandrov stated its question. So I'm not very sure if Aleksandrov was motivated by this result. Okay, so is a result due to Beckman and Quarles, 1950. It says that let f, okay, let n greater than equal to 2, and let f from Rn with Euclidean metric has the DOPP property. Okay, satisfies DOPP, then F is an isometry and hence affine. Okay. So this is this was the starting point of this talk. Okay, because I thought I should start with this. Now you see, so it says that in Rn, when n greater than equal to 2, if f maps and if f preserves distance 1, then f preserves all distances. Okay, so this proof is very interesting and very geometric. So at the end of the talk, so towards the end of the talk, I'm going to give you an outline of the proof. Okay, so but now we are going to move on, and we're going to tell you the results. So in other contexts. Okay, so that's so this is one thing. Now, once we see this, the next is this. Okay, in finite dimension. So what we saw is this: in one-dimensional case, Aleksandrov question has a negative answer when n is greater than or equal to 2. Aleksandrov question has a positive answer. So what about in the infinite dimensional case? Okay, by infinite dimension we mean, okay, with the Euclidean norm, that is all square summable sequences. In small L2, suppose you are in small L2, if you have a map that preserves distance 1, is it an isometry? Okay, now this is answered in the next theorem. So there exists a map so this is a notation that we are going to use to denote the space of all square summable sequences. So satisfying the OPP, that is not an isometry. Okay, so in the L2 case, I'm going to give you a brief sketch of the proof. So how to construct the counterexample, because that counterexample gives you certain questions which is still open. So I give you a quick proof of this theorem. Okay, the main part is to know that this is a separable space which means that it is a countable dense subset. So let S be a countable dense subset. Okay, so we find, okay, so fine, okay, it's a countable set. So step 1, what we do is this: we find a map phi, which is from L2 to S, okay, such that phi is identity on S, and distance between x and phi x is less than half for all x in L2. So you see, this phi is clearly so phi need not be continuous. In fact, phi is a discontinuous map. Okay, so now so what you do is this: so phi, it's identity map. Now by density, what you choose is this: you choose some phi x that is close to x, which you can choose. And now and in step 2, what we do is, in the step 2, we take this map, now define psi of x is 1 by square root of 2 en. I'm sorry, this is how to do that, huh? So En is the standard, so it's 1, 0, 0, 0, 1, 0, 0. These are the elements. So each separable, so each yn we map to 1 by square root of En. So now we are ready to construct a counterexample. So we define okay. So we define t of x. Okay. So then then we see this T is the map that preserves distance 1, then T preserves distance 1, but T is not an isometry. Okay, we should check that. Check. Okay. So, but then what? So why am I saying this? So why did I prove this theorem? You see, the construction gives you a discontinuous map that satisfies the distance one preserving property, but that is not an isometry. So the question is this: what happens if you add the continuity hypothesis? Suppose you know that you have you have a continuous map from L2 to L2 that satisfies a DOPP property that is not an isometry. So is it an isometry then? This is an open question, but we don't know. But what we know is this: if you add the hypothesis that this T is a homeomorphism from L2 to L2, then it is an isometry. So remark that 1, T is an isometry if we assume, so if we, okay, maybe I should write in a different way. How do I do this? Yeah, okay, fine. No, this is better. Okay. Just bear with me. This is my first talk on a tablet. Okay, so we say that we do have a positive result if T is assumed to be a homeomorphism. That's one thing. And the second one, so the continuous case remains open. Okay. So what we saw is, in one-dimensional case, Aleksandrov problem doesn't have has a negative result. Okay. When n is finite and n is greater than or equal to 2, Aleksandrov problem has a positive answer, that is a map that satisfies the DOPP property, a map that preserves distance 1, is an isometry and hence affine. And when n is infinity, that is in the case of small L2, then again the answer is negative. However, the answer is positive if the map is homeomorphism in addition. Okay, so now what we do is this: now we ask another question. So what about the case of different dimensions? For example, let's say that we have a map from R2 to R3, a map that preserves distance 1. Is T an isometry? Now here isometry means that isometry onto its image. Okay, so if you have if there is a map T from Rn to Rm, okay, and T satisfies distance 1, preserves distance 1, is T is an isometry? Okay, now this is the case. Now we look at the case of different dimension. Now different dimensions. So what we want to know, okay, so let M greater than N and let T from Rn to Rm satisfy the distance 1 preserving property. Is T from Rn to T of Rn, subset of Rm, is an isometry. Okay. So the answer is, okay, the immediate answer is, as you will see, is negative. But however, it gives you a whole lot of problems that have not been answered. That is one reason we are going to discuss the proof, and we will see this. So this proof gives you questions that have not been answered. So the answer is, so we will see this, maybe a result, theorem. I will give you a simple case. There exists a map R2 to R8 that satisfies the distance 1 property, but is not an isometry. So before I get to the proof, you will see the proof is very interesting, and the proof is very simple. It doesn't require anything more than high school mathematics. But okay, what we're going to do is this. Okay, maybe some remark. But before we get to the proof, let me give you let me write down a few remarks. Okay, so what's so holy about 8? The first thing, okay, there is nothing holy about 8, as you will see. Okay, so it is not known what is the least m greater than 2, of course, least m greater than 2, for which there exists a map T from R2 to Rm that satisfies the distance 1 preserving that property, but is not an isometry. So the question is this: can you reduce 8? Okay. So we will do a construction where you will see this. Why do we need 8? By using a slightly more clever construction, you can reduce it to 6. But then, can you reduce it to 5, 4, 3? We don't know. It is an open problem. So in particular, the one implies that it is an open problem. Now this, this believes to be a difficult problem if there exists a map T from R2 to R3 that satisfies DOPP but is not an isometry. Now this seems this is believed to be a difficult problem. When m is equal to 3 case, but even when m is equal to 4, 5, it is not known. Okay, so even I think this is to my best of my knowledge, m is 4, 5 are still open. So you'd be very happy if some of you think on this on problem and come up with a counterexample. So what we're going to do is, I'm going to give you a proof that how does one construct a counterexample when m is 8, that is when t lands in R8. So what we do is the following. The proof is very geometric. So we look at squares, okay? So we look at squares like this. Okay, the square with this left edge and the bottom edge included, but not the upper edge and the right edge. The side length is 1 by square root. So the diagonal is 1. Okay. So we take the squares of side length half, okay, such that these squares have this, the left edge and the bottom edge in it, but not the two other edges. And about vertices, only, I'm sorry. And only the left vertex at the bottom is a part of the square, but not the 3 other vertices. Okay. So what we do is this, using this square, we tile the plane. So what we do is this, we take this square, and what we do is, we tile this plane. In blocks of 9. We keep tiling this plane with these squares, okay? And then we number the squares. And how do we number the square? We just write it, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we tile the plane with these squares. So again, okay, maybe I do this part as well. Four, 5, 6, 7, 8, 9. So this way we okay. Now what we do is the following. Now we define the map. Okay. Now you see in R8. Now what is the relevance of R8? So on R8, and on R8. We have this standard basis, right? This E1, E2, E3 up to E8, right? 1, 0, 0, 0, 1, 0, 0 we have on R8. And we define what is called 0 to be the 0 vector. So on R8, we consider these 9 vectors, E1, E2, E3, E4, E5, E6, E7, E8, and then E0, E2, E0. Okay? So where do we stand? we tile the plane with the squares of side length 1 by square root of 2. Then I number this 1, 2, 3, 4, 5, 6, 7, 8, 9, and we keep repeating this number. Now this tiles, so this partitions the plane okay, nicely. Good. And on R8, we have this 8 linearly independent vectors, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, okay? And then we take the 0 vector. Now we define the map. Okay. So define from R2 to R8 by, we take a point fx, okay? So what we do is this, if x belongs to a square of number, let's say 3, we map it to E2. If the square, so if the point x belongs to, let's say, a square of number 5, we map it to E4. If x belongs to a square of number 1, we map it to E0. Okay, so and then we normalize it. Okay, if x belongs to a square e minus 1 numbered I. Now this is a perfect map, right? Because now the way we have chosen the square, it has partitioned the plane, so this map is well defined. Okay, now this is the map we would say we are looking for. Now clearly it is not an isometry, right? Because it is at 1, 1. Because if you take a point, so in a square with the same number, all these maps point to the same vector, right? So all points in squares numbered 1 gets mapped to 0. So this is clearly F is not an isometry. Okay. But now we show that if it satisfies DOPP, that is, okay, that is if the distance between x and y is 1, then the distance between fx and fy is also 1. So how do you show that? Let's see this. Yes,
sir. So what if the point lies on the vertex, one of the vertex of this square?
you see all these vertices are taken care of because each so I'm sorry, what did I do? So each each square has a so each, okay, one second, just I did something. Because this partitions the plane, okay? So this union, so it doesn't matter. Each vertex belongs to exactly one square, and we take that number.
Yes, I guess it was the picture you already had, which just got erased. You have two edges, and the dotted edges are not part of the square.
Yes,
Yeah,
yes.
yeah. So I think that was what you intended to show, but you.
Yes, sir. Yes, sir. Yeah, it is clear.
What? Okay.
Yeah, basically the edge is already covered. Yes.
Oh, you're talking about I'm sorry. Okay, your question is so. Shatidevan, is it clear?
Yes, sir. Yes, sir.
Okay. Okay. Now, how do we show that if is satisfied distance one preserving property? So let's take one. So let us take 2 points. B says that norm of it is 1. So what happens if the distance between x y is 1? You see, if the distance between x and y is 1, then 2. Okay, now I take 2 points, right? X and y. Now, if the distance is 1, then clearly they cannot belong to the same square, because that is how we have removed the vertices. Okay, and also the next thing that is observed that now where does 2 squares of same number lie? So let's say here we have 1, and the next one is here, right? In between we have 2 squares of side length 1 by root 2. So the distance between them is at least 1 by root 2 plus 1 by root 2 is root 2. Okay, so if the distance between 2 points is 1, which means that they cannot belong to squares of with same number. Yeah? That is how we have taken this square, so that and we have removed the vertices and edges, so that you don't have, so within a square you cannot have a point that you can have 2 points that lie at distance 1 and not, and then we have numbered the square so as to that the 2 points at distance 1 cannot be at squares with the same number. So once we see that, now with the 2 point x and y, then norm of fx minus fy is what? So 1 by ei minus 1 minus ej minus 1. What is crucial is this I is not equal to j, because x and y cannot belong to squares with same number. Once we have that, this is 1. Okay, so hence f satisfies the OPP. Okay. That's a counterexample. Now what you can do, now what you can improve the proof is this. Now instead of taking square, you can take hexagon, because hexagons still tile the plane. So once you take hexagons, then what you can do is this: you can have a map in R6, because you can take E1, E2, E3 up to E6, and then 0. So you can go to you can map it to R6. The problem happens with other dimensions, because the thing is, if you want to tile your plane with regular polygons, you will see this is the only way you can do it with triangles, square, hexagons. Okay, this 3, 4, and 6. So we run out of regular polygons if you want to tile your planes with okay. Now some remark. We say this map is continuous, is not continuous. So the question is, does there exist a continuous counterexample? Not known, open question. So it is not known if there is a continuous counterexample. We don't know that if you put continuity, whether Aleksandrov problem has a positive answer or not. We don't know. Okay. And what else? I just forgot something. Okay. And okay. 2. Using hexagons, we can construct. This is an easy thing. We can construct a counterexample. A from R2 to R6. So this is a nice exercise. Okay. Now, before I conclude, let me go back to the okay. Maybe so. Let me go. No, maybe I give you a few more open one more open problem, and then we will go back to the proof. So one open problem is problem. So what you take is now, what about what about other norms? 1, it is not known whether a map F from Rn, now I take with the L1 norm, satisfying DOPP is an isometry. Now, where this is very important, where when n is greater than equal to 3. So this analog of Beckman-Quarles result for the L1 norm case is open when n greater than equal to 3. Okay, so remark, in the L1 norm case, n is equal to 2 case has a negative answer. This is an easy construction, so maybe I leave it as an exercise. This, if you want, you can think about it. And what about in the L infinity norm case? Show that. So if you take this map, which is the max norm case, defined as, so this is the greatest integer function, okay, satisfies, has the DOPP property. Now this is clearly, so this is clearly not an isometry. Okay, so this tells you this, that the Alexandra problem is has a trivial counterexample when you look at the L infinity norm case. However, for the L1 norm case, it is still open when n greater than equal to 3. N equal to 2 case, it is so there is a negative answer. Okay, now before, so how much time do I have? Okay, I have 6 minutes. So I go back to this question, to this theorem of Beckman-Quarles. No, maybe I don't have. Okay, so I give you an outline. So I don't have time, so I can't prove it. Maybe I tell you an idea of the proof. So if you're interested in details, you can email me. I can send you the reference. Okay, I thought of doing this, but I have run out of time. So how does one prove this result, that when n greater than equal to 2 and f satisfies DOPP in the Euclidean norm case, f is an isometry? So this proof goes by the following way. So it's a very interesting. Maybe I write down the steps. Proof. In the step 1, what we show is this: if f preserves R, if distance R root 3. What it means is this: what the implication is this: f preserves arbitrarily large distances, right? R, it preserves R, then R square root 3, then R square root 3 times root 3. So it goes on. So it means that, so the implication is this: f preserves arbitrarily large distance. Then step 2 is f preserves distance 2. Now this is an intermediate step. Okay, this follows from step 1. The construction is same as in the step 1. Then step 3 says that if f preserves R and 2R, f preserves R by 2. Now, what is the consequence of, so if preserved R, distance R and distance 2R, then f preserves R by 2. So what it means is this: f preserves arbitrarily small distances. Why? Because we already know that f preserves 1. Step 2 tells us that f preserves 2. Therefore, using step 3, f preserves distance half. Now, f preserves distance half, f preserves 1. Therefore, f preserves distance 1 by 4. So this way we can go down and we can show that f preserves arbitrarily small distances. Now, and the step 4 is a general one. If there is a map that preserves arbitrarily large distances and arbitrarily small distances, then f is an isometry. It's a general result. The proof follows by showing that if is an isometry if f preserves arbitrarily large and arbitrarily small distances. Okay, so this is the rough sketch of the proof. This is not the sketch of the proof. This is the rough. So this is the main idea about the proof. And each step doesn't require anything more than school geometry. So the proof is very simple. You don't need to know any analysis, just no linear algebra. All that it requires is a property of equilateral triangles and rhombus and basically school geometry. A school geometry gives you an entire proof of this result. Okay, so I think that is where I'm going to stop. So the reason I wanted to talk about this result is because okay, so all the techniques. So this topic doesn't require any sophisticated machinery. Okay, it just requires some elementary geometry, maybe some elementary linear algebra. So I'd be happy if you want to study this problem and maybe you can come up with some with an answer of some open problem and like that. Okay, so if you are interested to learn more about this, you send me an email. I'm going to provide you references. I have okay. So yes. Okay, maybe I'll stop here.
Okay, so yeah, thank you, Saugata, for a nice talk and such a wonderful topic which was introduced today to the students. So are there any questions regarding the talk or regarding references? Yeah, Satvik, anybody, you can just go ahead. So Satvik, you can ask.
I just have a minor quibble about the construction from R2 to R8.
Okay.
So, what happens if, say, x maps to the 0 vector and y maps to one of your 1 by root 2 pi? Is the norm still
X
1?
map to, yeah. So 1 by root 2 vector means, 1 by root 2 is not there in the space. It maps in R8.
Right. So say you pick x from square 1 and y from square 2.
Okay. So if you map, so you take a point from you take what? You take a point in from E1. 1, right?
Square 1, yes.
Yes. And then you take it.
Yeah, distance 1 in square 2.
Yes. So what is the thing? What is the question? So
what is the evaluated norm after that? F of x minus fy?
Half and E1, right? Wait. What did I do? 1, 2, 3, 4, 5, 6. Okay, so it could be 1, but it is not an if and only if, right? Because the image can be 1, but that's fine. Are you there? It's not if and only if. That the distance between f and the distance between fx minus fy is equal to 1 if and only if distance between x and y is equal to y. It's not if and only if.
So the direction is from
one side. If the distance between x and y is 1, the distance between fx and fy is 1. not the other way around.
Yes, but even if the distance between x and y is 1, it doesn't the corresponding distance fx minus fy turn out to be 1 over root 2 in the case I mentioned?
No, because you have 1 by root 2 E0 minus E1. Now the norm of E0 minus E1 is root 2. So 1 by root 2 times root 2 is 1. See, you have E0 here, so you have E0 here, you have E1 here. I mean, this is an orthonormal basis, right? So the distance between any two, this distance between EI minus EJ is 1 by is square root of 2.
No, I guess his confusion is that you declared E0 to be 0, right?
Yes, yeah.
So
But that
then
does it?
E1 minus E0 becomes E1. I think that's where the distance. I mean, for all the other because it's a shift or something. I mean, your map will definitely work in
Yes, yes.
R9 as
Okay.
stated.
Oh no, I should have then started with the simplex, right? With the simplex in R8, where all the distance is same.
Yeah.
Really, I wanted
Right.
to, okay. Yeah, Shatik, you do have a point. So what we take is this, we take a simplex in R8 with 9 vertices, okay, and the distance between them is 1.
Right.
Okay. Shatik, but now I think I have lost them.
Would R9 make things cleaner by any chance?
Which one?
Say if you use 9 basis vectors instead of 8 basis vectors, if you moved up to R9, would that be cleaner? Then you'd have to dispense with the E0.
If I take R9, we take M up to EITUI. No, I think there will be a problem. Let me see. Let me see. Okay. Okay. Now I come to that. But first, does it answer? So have I answered your first question?
Yes.
So okay. Now R9 means So I want So E1 E2 En. I take EI to VI. It gives you a map, but then I want to reduce the dimension as so I want to have as small as dimension as possible, because once we have a map in R8, I will have a map in R9. Okay, Shatik.
Yes, I see. I mean, given that this map is slightly broken, perhaps R9 would.
But now once you have a map in R8, I can go to R9 easily. But then how do I write this then? So instead of saying this, or I should have said this, I take a simplex in R8 with side length 1, and then I should have mapped to each vertices of the simplex. Yes, thanks for pointing this out. I just oversimplified this. Thank you. Yeah. Is there any other question? But again, okay, no, fine. Any other question?
So I just have one maybe quick question regarding the last few steps, and just to see whether I understood correctly. You said that it's about equilateral triangles and rhombuses. So the first step seems like you stick two equilateral triangles.
Exactly.
Diamond, and then you say that the long diagonal is preserved or something. Is that the step?
Exactly. So what we do is this: we take this AB. This is our square root 3. So I take two equilateral triangles. Okay, side length R. Okay. Now, since it preserves distance R, it preserves the configuration, right? But then two things can happen: FA is equal to FB, or the distance between FA minus FB is R square root 3. Right? We have to rule out this case. Now, how do I rule out this case? Now that is okay. That is, I tell you, I take another point here, X. Now this is r square root 3 and this is r.
Okay.
Now ax, now similarly, so ff of a, so either fa is equal to fx or fa minus fx is r square root 3 using the same argument. Suppose fa is equal to fb. Okay, then what will happen? Suppose fa is equal to fx, then fa is equal to fb. But that is not possible because fb is equal to fx means because b and x are there at distance r.
Right.
Now, if fa is equal to fb, then distance between fb minus fx is r square root 3. Again, the distance is not preserved. We have a contradiction. So this long diagonal is preserved. That is the proof of the first step. Now, using the same technique, you show that it preserves distance 2. What is slightly non-trivial is to show that if f preserves distance r and 2r preserves distance r by 2, then you have to make construction using few circles and how they intersect and all that.
I see.
Okay.
Okay. Thank you.
Okay. And just I mean, long back I actually tried if we could reduce the dimension further. I'm telling this to I mean to students in case you have a new idea. The point is, so using square we'll end up in R8. Using hexagon we land up in R6. So can you use pentagon? But then in pentagon you cannot with regular pentagon you cannot tile the plane. Okay, but the question is if you can take some other combination now. If not regular pentagon, take some other pentagons and you arrange it in some clever way, and can you reduce the dimension? These are all open problems, so it's not known. People in general think that the n is equal to 3k. R2 to R3 case is very difficult. It's hard, but even it will be a new results if you have a counterexample in R2 to R4 or R2 to R5. That is even so that is not known. Okay, so I will stop here maybe.